Okay, so this is the second part of these introductory lectures on experimental techniques. And in this video, we're going to talk about cables and why you should care about cables. Okay, so it seems pretty obvious, really, that, a cable should transmit the signal. It really should go and keep the signal amplitude. It shouldn't distort the signal, and you don't really want your cable picking up extra signal from the environment, otherwise known as noise. So just how hard can this be? Well, if you look around a lab, the sort of typical things you're using in the experiment, then you'll see there are a variety of cables in use. So kind of one of the simplest cables that you're going to come across will be the 4mm so-called banana plug cable. These are cheap, they're simple, and they're okay if you've got large signals or you've got high currents you're dealing with. But as soon as you stop having kind of something that's a respectable current, several milliamps, amps, and voltages which are in the range of volts, it's going to get problematic to get a good measurement using a banana plug cable. Another type of cable you'll come across very frequently is the so-called coaxial or BNC cable. So this is a good general purpose signal cable. And in the BNC cable, what you have is you have a central conductor and then a layer of insulation, and then around that another conductor, and then finally the outer insulation and sheathing. And so what you see on the connectors at the end here is you've got the central pin, which is the middle conductor, and then you can see the white around that is the insulation between then the outer black conductor. And so a BNC cable is passing two signals, two conductors on the one cable, as opposed to the banana plug, which only had the one conductor per actual physical cable. Okay, another type of cable that's used quite widely is multi-core twisted pair cable. So this is particularly good when you're dealing with low frequency, low level signals and multiple signals on the same cable. So what it consists of is pairs of individual conductors that are separately insulated, and those pairs are twisted together, and then a bundle of different sets of pairs are wrapped together, and sometimes they come with an additional screening around the outside as well, as an example in this picture. And then, in fact, the picture here, this is taken of some Ethernet cable that's used for networking computers together. Another cable that's probably not so commonly used is the triaxial cable. So this looks like a BNC, but it actually has an extra layer of shielding and an extra conductor in it. So you have a central conductor, then a layer of insulation, then a middle conductor, then a layer of insulation, and then the outer conductor and the sheathing. And you can tell the triaxial cable from a BNC by looking at it, because the plug and the sockets have three locating keys as opposed to just the two on a BNC. And that's how you know that it's a triaxial cable. And if you actually look at it, then you can see you've got all three conductors there. And triaxial cables, as we'll see later, are very, very good for situations which you have low currents. So if you're measuring currents in the nanoamp, picoamp sort of range, then you'll almost certainly be using a triaxial cable. And then the final set of cables I want to talk about here are the semi-rigid coaxial cables. And these come with what are called SMA connectors. So these are physically smaller than a BNC, but they've got the same pattern. They've got a central conductor, and then they've got a insulation and an outer conductor, and then some sort of sheathing, and they terminate in these sort of screw fittings. And then these are particularly useful for high frequency signals. So when you're dealing with hundreds of megahertz to gigahertz sort of ranges. And the reason you make them semi-rigid is because when you're dealing with cables that are that size, you can't make your cable go round a corner that easily, because you'll end up having problems with your signal. And again, the way you make up these connectors here with these screw fittings, and you see they've got little hexagonal flat bits on them, you actually do them up with spanners. And again, that's critical to actually making them work well. So why do we have these different types of cables, and why you pick one cable rather than another one for different situations? So we can think about a cable in terms of an equivalent circuit. So we can then think of what a representative section of a cable might look like. And so what you're going to end up with is an inductance per unit length. You're going to end up with some resistance in the cable per unit length. You're going to end up with a capacitance between, if it's if you've got a signal line and a return conductor, or like in the BNC or the triaxial cables, or between two cables if it's a pair of banana plug cables. You get some capacitance there, and you potentially get some leakage conductance as well. And so we can actually go and do an analysis of what's going on with these sorts of situations. Okay, so here's our elemental bit of cable then, with our inductance, our resistance, our capacitance, and the leakage resistance, which we're going to write as 1 over G, the leakage conductance. And we say here is a position X, and here is a position X plus delta X. So we can write down now what the voltage drop and the current going through this circuit from here to here is going to be. So we can start with a voltage. We're going to start with the voltage at X minus the voltage at X plus delta X. And that's going to be given, so this is just applying Lenz's law. So the inductance, which is L times delta X, because remember L is per unit length, dI dt, plus the resistance, delta X, times the current from Ohm's law. And so we can say that's minus delta V is L. We make that minus delta V over delta X becomes L dI dt plus R times I. We'll call that equation 1. And we can do the same with the current. So we can write down I X minus I X plus delta X. And that is going to be equal to the capacitance per unit length times delta X dV dt. Plus the leakage conductance delta X times V. And similarly to what we've just done, we could write minus delta I delta V, delta I delta X even, is equal to C dV dt plus G times V. And we'll call that equation 2. Okay, so what we're going to go and do now is think about differentiating these two equations with respect to X again. So we're going to take the limit that this is, in equation 1 is dV dx. So I'm going to do d1 dx is equal to d2v dx squared di by dt plus R di by dx. And then we'll note we can change that to being L d by dt of di by dx plus R di by dx. And then that is di by dx L d by dt plus R. So strictly speaking, I should write it the other way round. And now what we can do is we can substitute in from equation 2. And so what we're going to go and do is we're going to take our second equation here, and we're going to put in these values. And what we'll find out is we've eliminated the current from this equation. So we're going to end up with d2 dv dt squared is going to be, gather the terms all together, see, actually let's write the first bit from here first. So L d by dt plus r times, and this part of it, c dv by dt, I'll move the minus sign there, plus gv, and so that becomes minus lc d2v dt squared, and then there's a term there, rgv, and then there's two terms in terms of dv dt. So we have one which is L, G, and the other one which is R times C. Okay, so what does this equation mean? Well, if we go back to our element here and then think what an ideal case would look like. An ideal case would have no resistance in our cable there at all, and would also have no leakage. And so R and G would both end up being 0. So if we look at that case, we're going to lose that term. We're also going to lose that term. And therefore what you end up with is d2v dt squared is minus lc d2v dx squared. Whoops, dx squared there, sorry. So that is actually describing a wave equation. So that's the sort of standard equation you'd expect to go and get for a wave. Okay, so if we did the same operation with the other equations, if we differentiate equation 2 with respect to x and substitute in the value from equation 1, then you'll get an equivalent equation in terms of the current, and you'll show that d2i dx squared Okay, so we create our equation d2v dt squared is minus lc d2v dt squared. So solutions to these type of equations are going to be traveling waves. So we can write v is v naught e to the I kx minus omega t. So that's a standard traveling wave written down in as a complex exponential. And so if we go and do that, what you can show therefore is that d2v dx squared becomes minus k squared v, and d2v dt squared, oops, actually let's make that plus, is minus omega squared v. And that is obviously LC d2v dt squared minus omega squared. Oops, minus sign there. And so what we have, the v's now cancel, and we have that k squared over omega squared is equal to LC. K over omega is therefore LC the half. And in fact, it's more useful if we think about it in terms of omega over K. Minus a half. Why is that useful? Well, come back to what you've done in first year waves in physics 2. Omega over K is the phase velocity of a wave. So we can identify this as the phase velocity. And if we think about what the omega by dk would be, so d omega by dk is the group velocity, and that's also LC to the minus a half. So this is telling us that the phase velocity and the group velocity are the same. So as we just saw, we have if we take the resistance and the conductance both to be 0, so making an ideal cable, then the characteristic impedance of the cable gives us a very simple wave equation. We know that solutions of this are the complex exponential form, and we can identify the phase velocity and the group velocity, and they're both to be given by 1 over the square root of the capacitance times the inductance per unit length. So the next thing we want to go do is think about the impedance of the wave. And so what we will do is we're going to take the differential dv dx, and that becomes I k times v. And if we keep the resistance equals 0 from the equation we derived earlier, then we know that that is simply minus L di dt. So now we can go and integrate things. So we're going to integrate and do di becomes I k over L, the integral of v, which is v naught e to the I kx plus omega t, whoops, dt. Okay, so what I've done here is I've just taken the dt across to this side and the L across as well. So this just becomes the current. And if you evaluate that integral, then what you end up with is simply k over omega v over L, and that bit there we can write v over I equals L omega over k becomes the square root of L over C, and v over I is of course the impedance. So that becomes the impedance, which we'll call Z, of our cable. So what we've done is, just by keeping this as a perfect cable, we get the basic wave equation as a wave-like solution. That incidentally is telling us that we can propagate waves down this cable. That's how we expect to have it working. We can find a phase velocity, we can find a group velocity, and we can find the impedance. And we find that all of these quantities are just defined in terms of the characteristic inductance and capacitance per unit length. Of course, if you have to introduce a real cable with a real resistance here and some real leakage G, these equations get more complicated, but the basic analysis we've done still holds true. Okay, so to summarize on what we've just shown, in the case of the perfect cable, we've got the impedance, root L over C, for a voltage with a traveling wave type form. And there is a relationship between the frequency and the wave number, which is not dependent on the frequency or the wave number. So in other words, the phase velocity and the group velocities are equal, and at Z over L, which is what you'd expect from standard study of waves that you did in first year. Now, the important significance of this is that it means that the group velocity of the waves doesn't depend on the frequency, and therefore there is no dispersion. So what happens, therefore, is a wave traveling down the cable is not distorted. So the cable is not distorting the signal, at least in the case where R is equal to 0 and G is equal to 0. Of course, if that's not true, then your cable is starting to disperse and distort the signal, and that's not a good idea. So you really want fairly obviously, you want your cables to have a low resistance and not to leak. Note, however, that does not mean the cables have zero impedance. So the impedance is Z is defined as the driving force divided by the response, the voltage over the current. That's the same concept of wave impedance that you met in physics 2. And you should note that that wave impedance is given in units of ohms. If you actually sit and do the dimensional analysis of inductance over capacitance square rooted, then you'll find that that actually has a unit of ohms. And so we talk about the impedance of a cable in a certain number of ohms. We don't mean it has a resistance. What we mean is that the ratio of the capacitance and the inductance is at a certain level to give you that impedance. Now, coming back to how things work with waves, if you remember about wave impedance, if you changed wave impedance, then you get reflections. And the same is true as what's going on with cables. If you have a mismatch of impedance, then you get a reflection. And this can happen, for example, at connections and also at the ends of cables. So if you actually work through the numbers, then if you look at the BNC and SMA cables, they both have a characteristic impedance, typically of 50 ohms. So in other words, their inductance and the capacitance are such that the square root of the ratio of them is 50 ohms. And then if you look at the back of instruments, what you'll see is things are marked up as having 50 ohm inputs and outputs. And what that's telling you is that if you attach a 50 ohm cable to that connector, then you're not going to get a reflection at that connection. But you can also get reflections at the ends of cables, because obviously air does not have a characteristic impedance of 50 ohms. So if you're at the end of a cable, what your electrical signal will see is a massive change in impedance, and you'll get a big reflection coming back at you. So to avoid this, what you can do is put on what are called so-called terminating resistors. And that's literally just a 50 ohm resistor that's connected between the inner and outer connector of the BNC cable. And its purpose is to stop the signal reflecting back down the cable at you. And instead it absorbs the signal. And so as far as the signal traveling down the rest of the cable is concerned, that cable could be infinitely long because it doesn't ever see any reflection coming back. So then you also need to think about how your cables might influence the amount of noise you see in an electrical signal. So there are three types of ways you can get noise in a cable. So first of all, you can think about capacitive coupling. So in this case, cables are acting like antennae. They pick up some high frequency electrical signals. So the classic ones these days are mobile phones, Wi-Fi, but also includes other experiments. And it can also include sudden sparks as well. And what happens is that the inner and the outer connections, the cable will pick up that high frequency signal from the environment, and they'll see it as a voltage. You're essentially charging the cable as though it's a capacitor. And the way to avoid this being a problem is to make sure that the plus and minus conductors on the cable, or the signal on the ground, see the same electrical frequencies and the same electric fields, and then they both vary up and down by the same amount. And so because you're measuring typically the difference between the two conductors, you don't see the amount of noise you generate there. That's not entirely perfect because although we say we're measuring the difference, what you're often actually doing is measuring the voltage between ground and the inner conductor and ground and the outer conductor, and then looking at the difference between those two measurements. And if your signals are fluctuating, if your whole cable is moving rapidly up and down in voltage, then you can actually have problems with the way those two measurements are then subtracted from each other. So a better alternative is to screen the cable with a conductor that's well connected to ground, so that any capacitive pickup is shunted down to ground and doesn't influence your electrical signals at all. So this is where you might be using, say, coaxial cables, particularly triaxial cables, but also it's why you screen twisted pair cables as well. So the screening is stopping the problem with the inductive, with the capacitive pickup. In the triax cable, it's the outermost conductor that's screening the inner two conductors. In coaxial cables, you might have simply the outer of the cable being the ground, the screening, and then the inner is your signal lines. Whereas something like a banana plug is hopeless in this because there's no screening possible. So the next type of noise problem you can get is an inductive pickup. So if you have any gap between the plus and minus conductors in the cable, then it's going to form a loop. And any kind of time varying magnetic field that passes through that loop is going to induce a voltage through Faraday's law of induction. And so that's going to appear as noise. And this is particularly a problem where you have low frequency and large currents involved. And the classic one there is mains electricity. But you can also get problems from power supplies, and particularly transformers and coils and speakers are all great sources of inductive noise. So how you have to be able to defeat that is to reduce the size of the loop between the plus and minus terminals. And this is where twisted pairs come in. So each time you twist the cable, you form a little loop, but then the next twist undoes the effect of that loop by reversing it. So the twisted pairs then have a minimum amount of area between the two conductors, and that's how they're avoiding inductive pickup. So then the final problem is contacts. So contacts can be a source of noise in a cable in a variety of different ways. So first of all, if you have very high resistances, then you get an effect of shot noise, which we'll discuss in the noise lectures. So that's the case where if your conductors that are joining up your cable have got horribly corroded or something and are not making a good connection any longer, you have a lot of oxide on the connector there. If you have a non-linear contact resistance, then you're going to distort the signals because the impedance for a positive signal is different from the impedance from the negative signal, and that's going to cause horrible problems. And then in particular, if you don't have a stable contact resistance, then you get some kind of time-dependent impedance mismatch, and that really is also going to introduce a lot of noise. And then the final thing is that you can make a thermocouple by accident. So if you have a join between two different metals, then you're going to get temperature-dependent effects due to the Seebeck effects. So all of these combine to say that what you really want to go and do is choose something that's metallic, low resistance, and chemically inert. And of course, the classic metal for choosing that is to go and use gold. And this is why high-quality cables are gold-plated. If, however, your signals are large digital voltages, then gold plating is a bit of a waste of time. So if you're buying gold-plated digital cables, someone's trying to pull a fast one on you, but buying gold-plated analog cables might actually be a useful thing to be doing.